NVIDIA's quantum leap, supercomputers set to revolution the future. NVIDIA's latest supercomputers are pushing the boundaries of quantum computing, and the implications are staggering. We are on the threshold of a new era, but are we really ready for the next events? In a dimly lit room, rows of humming machines emit an eerie blue glow. These are no ordinary computers. They are the forerunners of a new revolution. 1. In one of the most unlikely alliances we'll ever explore, Nobel meets Silicon's image of the physicist celebrated for unlocking the secrets of complex systems, shakes hands with engineers from a company best known for game graphics. This is the fact that behind NVIDIA's success in quantum computing is Nobel laureate Giorgio Prezzi. He was working on the theory of spin glasses and was not looking to revolutionize computing. His focus was on understanding the strange behavior of some materials at the quantum level. But when NVIDIA noticed his research, they saw an opportunity to turn that result into a partnership. This unlikely alliance isn't just about academic curiosity. It also paves the way for quantum computers to solve problems that our current technology can't even begin to solve. We're talking about optimizations that could revolutionize everything from drug discovery to financial modeling, but not everyone is convinced. Critics argue that quantum computing has been around the corner for decades. Are we really on the verge of a breakthrough, or is it just another blunder? To NVIDIA, the company that supplies powerful graphics cards for the latest video games, is quietly spinning behind the scenes. They're betting big on quantum computing, and it's a gamble. Redefining the DET technology landscape in 2023, NVIDIA invests a staggering $1.2 billion in quantum research. The development more than doubled their investment from the previous year. Why the sudden urgency of the answer lies in the growing understanding. How small can we make transistors? Instead of relying on binary bits, quantum computing offers a way out of this impasse. Interestingly, they are not trying to build quantum computers from scratch, but rather using their existing GPU technology to simulate quantum systems, a bit like using a flight simulator to design better airplanes. Quantum systems on classical hardware will never be as efficient as building real quantum computers, but NVIDIA advocates point out that emulation allows for rapid iteration and testing of quantum algorithms without the need for expensive specialized hardware. It limits providing valuable insights that could accelerate the development of true quantum computers, and if NVIDIA's gambit pays off, they could find themselves at the forefront of the next computing revolution. The research that has caused such controversy is at its core. 3. Something called the Ising rotating glass model. This concept is simpler than it sounds and is the key to understanding the potential of quantum computing. Imagine a flat surface covered with tiny magnets, each of which can point up or down in a regular magnet. All these tiny magnets are aligned in the same direction, but in a spinning glass, it's chaos. The magnets interact in complex ways, creating a chaotic system that Fischlin-Weid supercomputers enter, because many real-world problems can be mapped onto this type of map. Simulating these systems is incredibly computationally intensive. A spin glass model with the size of states can have more possible configurations than there are atoms in the universe. Classical computers struggle to handle this complexity, but Quantum Anus is a special kind of quantum computer, which is made for this type of problem. The research team used NVIDIA GPUs to simulate how these quanta behave by slowly tuning the system until it settles into its lowest energy state, effectively solving the problem. Spinning glass's dramatic change may seem abstract, but it has profound implications, showing that quantum mechanics can be much more effective at solving certain kinds of problems than previously thought. We're talking about potential speed-ups, which can turn a month's worth of calculations into minutes. But while the simulations are promising, they're just simulations. The real test will come when we can build quantum annas big enough to tackle these problems in practice. And this is still an important challenge. Explore the power of tomorrow with NVIDIA. Subscribe for more updates. 4. The hidden cost of quantum supremacy. There is excitement around quantum computing, but there is a darker side to this technological leap that we must address: the environmental impacts of quantum computers in their full potential. The environmental effects of quantum computers with all their potential are energy. The current generation of quantum processors must be cooled to near absolute zero, which is colder than deep space. This cooling process consumes about 25 kilos of energy. That's roughly equivalent to the energy consumption of 20 average American homes, and that's just for one car. Now imagine scaling that up to the processing power of current supercomputers. A computer can consume as much energy as a small city, which raises the troubling question of whether we are solving one problem only to exacerbate another. Are we inadvertently accelerating climate change? The approach of using GPU simulations. By simulating quantum systems on more efficient classical hardware, we can make progress without the extreme energy costs of full quantum systems. But even this is not a perfect solution. Leonardo's facility in Bologna, consuming about 10 megadollars of energy in peak operation for this research. That's enough to power several thousand homes, and this was just for simulation work, where real quantum computing at this scale would likely require much more energy. On these materials, which are often mined under questionable environmental and ethical conditions, as the demand for quantum hardware increases, the quantum computing community is aware of these issues. Research into more energy-efficient quantum architectures and cooling methods continues. 5. A 2023 report by the Quantum Economic Development Consortium estimated that the quantum industry will need 50,000 to 100,000 skilled workers by 2030. Currently, we are nowhere near the demand. Why there is a lack of quantum computing in this field. The intersection of several complex disciplines of physics, computer science, mathematics, and engineering. Finding people with expertise in all these fields is like looking for a quantum needle in a haystack. NVIDIA research collaboration. This highlights the issue. The team included physicists, computer scientists, and hardware engineers. This multidisciplinary approach is becoming the norm in quantum. Research shows our education system isn't keeping pace. Universities scrambling to develop quantum computing curricula. The field is evolving rapidly so that by the time a 4-year degree program is established, parts of it may be out of date. As quantum computers become more powerful, this has real-world implications. They can break many of the encryption systems that currently protect our data. We need a new generation of them. There is also the problem of access for cryptographers to develop quantum-resistant security measures. Quantum education is currently concentrated in a handful of top universities. Tech hubs risk exacerbating inequalities in the tech industry, as some companies take matters into their own hands. For example, IBM has launched a quantum education initiative aimed at high school students. 6. A quantum education initiative aimed at high school students. NVIDIA offers free online courses on the basics of quantum computing, but these efforts, while laudable, are just a letdown. An ocean of what's needed. The 6 quantum double-edged swords of security in a post-quantum world as we marvel at the potential of quantum computing. The shadow looming over the horizon, technology that promises to revolutionize fields such as drug discovery and financial modeling, is also a problem. Quantum computers are becoming a reality. It is not enough to develop quantum resistance algorithms. We need to deploy them in our entire digital infrastructure. This is a very important task that requires cooperation between governments, technology companies, and cybersecurity experts. Collecting encrypted data with the goal of deciphering it when quantum computers become powerful enough means that sensitive information we send today could be compromised years from now. Quantum technology offers new tools for cybersecurity. Quantum key distribution, for example, promises communication channels that are theoretically unhackable, but implementing these systems on a large scale has its own set of challenges. This far, let us know what you think in the comments section below. For more interesting topics, make sure you watch the recommended video that you see on the screen right now. Thanks for watching.